Right, so we study exponential functions and its inverse. It's called the logarithm function. Now today we are going to study inverse trigonometric functions and including their derivatives. So this the most important two functions will be sine and cosine and tangent. So we are I'm going to spend a little more time on those two sine and tangent functions. So the sine function is defined on the whole line. So itself, it's not the inverse function. So it is not an increasing function, decreasing function. So it does not have inverse in general. However, if we restrict the function to an interval which is from negative pi over 2 to positive pi over 2. Yes. Right. Then the graph of this function is an increasing function. Okay. So this is a piece of the graph. So over that interval, the function is increasing. So therefore, the inverse exists. Okay. So the inverse exists. This function, yeah, is increasing. Okay. So the inverse exists. So here you have x, then you get a y, but conversely, you get a y, then get an x. So x is going to be, let's see, how can I describe the inverse, right? Sine to the -1 and the y, okay? This is the y equals sine x. So you back forward. So I cannot express x in terms of y using elementary function. So I have to create a new symbol, right? So, you know, if it's f, then f to the -1, right? F -1 is going to be the inverse function, right? That's it. So this is the inverse function, and we try to understand. And those two equations are equivalent. But if you want to draw the graph for y equals sine x, you know, exchange two variables, then the graph will be somewhere here. It goes looks like that. Okay. And the domain will be from -1 to +1, and the range will be from negative pi 2 to positive pi 2. Okay. We obtain this graph by refracting the sine graph around the line y equals x. I'm more interested in the derivatives. Very curious about the derivatives. How do I find the derivatives? I think we already have the formula. The derivative of the function, or you can use, yeah, f prime, right? According to the formula will be sine prime and this, right? Sine prime is going to be cosine. So we get this formula. Okay. So that's the derivative of the inverse function. The problem is it's too complicated, cosine sine, right? So how can I get rid of sine x, you know, the inverse function? It's possible here. Right? So how do you do that? Well, sine of this x is called theta, right? Now what does that tell you? Tell you two things. Sine theta is going to be x, no problem. But there's also restriction for theta. Theta is between negative pi over 2 and the positive pi over 2. Okay, so arc sine x equals theta means two things. Sine theta equals x, and theta is between these two numbers. Because theta is in the fourth quadrant and the first quadrant. So cosine theta is going to be, this implies cosine theta is going to be positive or 0. Okay. Why? Because cosine value is positive or in the fourth quadrant and the first quadrant. Okay. But that's good enough. And then cosine, because of this sign, it's going to be 1 minus sine theta square, right? You agree? Otherwise, it will be plus minus square root of 1 minus sine theta square. Right. All right. But I already know sine theta. Sine theta is x. So it's square root of 1 minus x squared. All right. So cool. So what I get here, I'm going to put it here, right? And because cosine theta is arcsine, so so it's going to be square root of 1 minus x squared. Okay. Yeah, this is a cosine theta. Okay. Cosine theta. Because theta is arcsine x. All right. So this is what we get. Now, similarly, I don't want to do with I don't want to do the cosine. For cosine, we have you can do a similar argument, okay, to get a derivative. Okay. Now, y equals cosine x. The only problem is you have to find the interval for cosine x so that it's increasing, I think, or decreasing. We use this piece. Okay, here's a pi, here's a 0. That's a decreasing function. So decreasing, so the inverse exists. If you have an x, you go up, you get a y equals cosine x. But if you get given y, I can get the inverse. Okay, so that's the inverse. But the graph of the cosine, arc cosine, y equals arc cosine x, should get a graph by rotating. Okay, so how can I do that? I'm going to rotate this point. It's harder to draw it. Okay, I think it looks like that. Okay. Yeah, it's a symmetry about this line. So my graph will be like this. Okay. Right, this is going to be the point 1. That's going to be point negative 1. It's a 0, and here's a pi. Right. So this is the inverse function. And for the same reason, the derivative of arc cosine, we can get negative 1 over 1 minus x squared. Okay, so by similar argument, I'm not going to go through this. Same argument. Okay, by similar argument as above. Yeah. Okay. There are other inverse functions. Let's using those two inverses to to do some exercise. Okay? Let's before we continue, work on arctangents. Let's do some exercise first. Find the exact value of each expression. So this is a okay. From the graph, right? So you're looking for the value if this is theta, right? So you know sine theta is going to be 1/2, and theta is between negative pi over 2 and positive pi over 2. I think that's only unique solution there, which is pi over 6. Okay, sine pi over 6 is going to be 1/2. So in this case, yeah, theta is going to be pi over 6. Okay, there are lots of problems involve tangent, so I have to go back to tangent. I have to use that. Yeah, otherwise I'm not able to do any problems. So the tangent, yeah, let's look at the tangent x. Okay, so how do you draw the graph? Well, there are many pieces of that, right? And it's going to be here's pi over 2, negative pi over 2. So this is a graph of a tangent function. So this piece is always increasing. So the inverse exists. Okay. Here's a y. Here's x. If you give x, you get a y, tangent x. But if you get given y, you get the inverse, which is denoted by tangent, arctangent y. Okay. Yes, let's derive the formula for the derivatives. Okay, so you can get the equation y equals arctangent x. How can I do that? You just reflect the graph about this line, right? So actually, it is going to be like this. Okay, it is between -1 and +1. These two asymptotes. So the domain for the arctangent x is from -infinity to +infinity. So let's find as the derivatives. According to our definition, according to our formula, that's the derivative of tangent, right? The only problem here is how do I get rid of the tangent in the final expression? This is correct answer already, but we have to simplify some of this. Okay, so if you denote this by theta, okay, again you have two things. Tangent theta is going to be x, and the theta is between pi over 2 and the negative pi over 2 and the positive pi over 2. So we want to find out, what is the derivative of tangent theta? Derivative of tangent theta is going to be 1 over, I think it's a secant square, right? But its secant square is in the denominator. So you get cosine square tangent. Okay. So we are given arctangent x, which is theta. We want to find out cosine square theta. Right? This is going to be theta. Okay. How it is related, cosine theta and sine theta, how is it related? I think it's 1 plus tangent square theta is going to be 1 over cosine square theta. Guys, that's a relationship. So cosine square theta is going to be 1 over 1 minus tangent square theta. But tangent square theta is going to be 1 plus x squared. Okay. So if we solve the problem, we put it here, we get okay, so that's what we get. So this is our form. Okay. By similar argument, we get the derivative of cotangent, arc cotangent x. Okay, so just differed by negative sign. Arc cotangent. Yeah. For arc cotangent, the only difference here is going to be negative sign. Okay, negative of this by similar argument. And now we can do all kind of exercise. All right, so we the arc cotangent. Well, what's the domain of the arc cotangent? I think it's cotangent x is from 0 to pi, and this is this is going to be in decreasing function. Here's a pi over 2, because y equals cotangent x will be cosine x over sine x. So when x equals pi over 2, y value is 0. When x is greater than pi over 2, y value is negative. Okay, so the inverse exists. So the inverse will be draw this line, right? And turn it around. I think this will be something like that. Okay, it's pi over 2. Wait a minute, it's pi. So cos, no restriction x. Yeah, you just turn this, reflect this graph about the line y equals x, and this is going to be this is a graph y equals cotangent. Okay. Yes. All right. So this is pi, and here's a horizontal. All right. So now let's try to find the exact value of several problems here. Okay. Find the exact value of this. Oops. Okay. All right, so we have to be careful about this is a number, right? Arctangent x. Now, what is this is not going to equal 3 pi over 4, okay? Because for the tangent x, the output is always between negative pi over 2 and the positive pi over 2, okay? For arctangent, look at that, right? For tangent, arctangent, okay? This is that was a mistake. Okay, so it's always between, the output is always between negative pi over 2 and positive pi over 2. So in general, before we do that, we have to understand So when this holds, okay, when this holds, okay, this holds only for x between negative pi over 2 and the positive pi over 2, okay, in general. So you cannot apply this to that problem because x is over 3 pi over 4 is beyond the, yeah, is outside of this domain, okay? Okay. So in order to simplify it, you have to compute the one inside first, okay? Tangent of 3 pi over 4. It's going to be -1. Okay, can you see that? Okay. It is angle here. Okay, so cosine is going to be, cosine of that angle is going to be negative. Sine of that angle is positive. The ratio is going to be negative. If you only memorize the values of sine and cosines on for special angles, then you can use that to get the values for tangent. Okay. So then this is going to be, okay, it's going to be negative pi over 4. Okay. Yeah, this is going to be negative pi. So it is not going to be 3 pi over 4. It's going to be negative pi over 4. Why it's a negative pi over 4? Well, you just, if you don't remember the graph for arctangent, so this is a tangent, right? The value here is -1, then there's a corresponding angle must be negative. So negative pi over 4. So for the positive value, you get a positive pi over 4, right? Yeah. So when tangent of pi over 4 is going to be 1, tangent of negative pi over 4 is going to be -1. So that's the reason arctangent -1 is going to be negative pi over 4. Okay, so next question. Cosine 2 of this. Okay, let's try to get the exact value without using calculator. Okay. So this is the angle, all right? So we know that sine of 5 or 15 equals theta. We want to find out cosine 2 theta, right? Basically. Right. So I know two things. Sine theta equals 5 over 13. I know theta is between negative pi over positive pi over 2. But actually, clearly this theta must be between 0 and the pi over 2, okay? Okay. That's fine. So how can I get a cosine 2 theta? I have to use the formula cosine 2 theta equals cosine square theta minus sine square theta. I can use 1 minus 2 sine square theta. Okay. Okay, because I already know sine theta. Okay, I got this. Okay, then you simplify it. 1 minus 50, 169. Right? So you get 119, 169. So you get this value. This value cannot be larger than 1. Right, so that's all about the exact values. Now we want to find out the derivatives now. Okay, so let's do problem number 22. Okay, find the dy over dx. According to the chain rule, right, what we know is the theta tangent, right? Not theta. I'm gonna dy. No, don't use the same y here. Okay. Let's say u. This is going to be 1 over 1 plus u squared. And we know this formula, so we just use that formula to find the derivative. Okay. So dy over dx, okay, according to chain rule, you can do it directly, right? So what u is going to be x squared. Okay, u is going to be x squared, then square, and the derivative of u is derivative x squared. Okay, so you get 2x 1 plus x to the 4th power. So that's it. The next one, y equals cosine, cosine, here's sine t. Well, find the dy dt. Well, you can express in the form like that, and u equals arcsine t, right? So by the chain rule, dy dt is going to be dy with du and du dt. Right. The derivative of y with respect to u, it's going to be negative 1 minus u squared, and the du over dt is going to be positive 1 over square root of 1 minus t squared. So now you have to replace u by 1 minus arc sine t squared. So this is answer. Okay. This is answer. Okay, so next one. Find the derivative with respect to x. All right, so let's do it. Well, you don't need to introduce an intermediate variable, but this time probably we should do separator. Yeah, so we introduce the variable u, and the u is going to be x. Okay, I'm going to find the derivative of u with respect to x first, which is 1 minus. Okay, this is the x minus 1 plus x squared to the 1/2. So when you differentiate, you get here's 1/2 and x 1 plus x squared. 1/2 minus 1 is negative 1/2, and it's 2x. Oops. That's weird. I accidentally clicked the. All right. Right, so we differentiate this with respect to x, and then you simplify, you will get the 1 minus x and square 1 minus x. Okay. So now dy over dx is going to be dy of du and du of dx. So for the tangent, arctangent of u, I know that's 1 plus u squared, right? And that is du of this. It's 1 minus. So is that enough? Not sure, right? Let's continue. So we have to simplify all this, right? It's 1 plus x, 1 plus x squared and a square. Yeah, I'm not sure we can simplify it further. Let's square it. Okay, you will get 1 plus x squared minus twice x times and plus 1 plus x squared. And here I can and maybe we can simplify it. I got double. You were surprised, right? I got a double x squared, double of this. So what I can get is I can take a 2 out. 1 plus x squared minus x times 1 plus x squared. Okay? All right, I think we can simplify. So what I'm going to do, I take 1 plus square 1 plus x squared out. Okay. Well, so this cancelled out. The answer is very simple. Yeah, surprised. This answer is just equal this. Right. Right, so the next part, f of x equals arc sine e to the x. Okay, we want to find out the derivative and the domain of the function and its derivative. Okay, look at this. Arcsine. What is the domain of the arcsine? The domain of the arcsine is going to be from -1 to +1. Okay, So look at this, the domain of the arcsine. Right? Y equals arcsine x. So that means the arcsine only takes values on x between negative and positive one. So that means the domain of f are those x, e to the x is between negative one and positive. Right? But e to the x never be negative. All you have to do is x is less than equal to 0. That's it. E to the x less than equal to 1. X is less than equal to natural log of 1, so it's going to be e to the x less than equal to 1 implies x less than equal to natural log of 1. Okay, which is 0. You can see that from the graph. All right, so that's the domain. So we find the derivative of the function. So arcsine, the derivative is going to be square root of 1 minus of e to the x squared. Then you have to differentiate e to the x, which is the same. So that's why it's e to the x. Okay. Then we work on some implicit differential method. Yeah, using an implicit differential method to find the derivatives. So find the y prime if arctangent of x squared y is going to be x plus xy squared. Okay. So it's differentiate both sides with respect to x. So you put derivative. Right, on both sides. So the derivative of arctangent is going to be 1 plus this whole thing, right? But don't forget, you have to differentiate the inside part. So x squared times y. And here, that's right. So here, you have to differentiate the second part. Now, apply the product rule to this problem. The product, the first part is 2xy, then x squared dy dx. And here is 1 plus x squared plus x times y squared is 2y and dy dx. So there are 2 terms containing the derivative. Yeah, a little bit complicated. We have to be careful. So you have 2xy and plus let's use y prime here for convenience. So now I have those 2 terms I have to move together. Okay, I move those two together. Okay, and then I move the other term to the right hand side. So big parenthesis. Right. Finally, we solved the problem. Yeah, it's tough. So y prime now, whoa. Okay, and here's x squared over 1 plus x squared y squared minus 2 times xy. Okay. Should you simplify it? Of course, you have to simplify. This is a giant fraction. Okay. You have to, yeah, wait a minute, which, yes, 1 plus, yes. So this common denominator, you have to at least write down like this. So it's 1 plus x squared y and square minus 2xy. And this is x squared minus 2xy, 1 plus x squared y squared. Okay, so that's enough. I don't think you can simplify further. At least you only have one fraction. I don't want to see fractions inside fractions. I did not expect this is so complicated problems, yeah. But just you know, in each step, just be careful with the computation. All right. Right. So now we come to the integral, right? I know the derivative of arcsine x is going to be this. So that is really equivalent to saying that if you see the integral like this, it's going to be inverse plus constant, inverse sine x, arcsine x plus constant. Okay? And similarly, I don't want to use a cosine because you the only difference is just negative sign, right? Similarly, right? Then it is equivalent to okay. Then I discovered something special. When I add those two together, I find out it's going to be 0, right? Because when added together, one is a positive, 1 over square 1 plus x square. Another one is negative, 1 over 1, right? So that means if some function, the derivative is 0, then it must be constant. Okay, what is the value of that constant? You just look at x equals 0, right? In order to determine the value of constant, the constant is going to be arcsine 0 is 0. Arc cosine 0 is going to be pi over 2. Okay. So in other words, we always have this identity. Okay. So there's no big difference, arcsine and arccosine. Okay. They're both defined on x between negative and positive. Negative and positive, yeah. So essentially, the arc, cosine, sine are no bigger than. They differ by a constant. All right. But the derivative of arctangent x is going to be 1 over 1 plus x squared. So this, if you next time if you see the integral like this, you just need to write down, hey, this is arctangent x. Okay, I think that's the motivation to consider inverse trigonometric functions and their derivatives, because we find out 1 over x. You know, if we want to integrate 1 over 1 plus x squared, okay, we can express that integral using the inverse function. Okay. All right. So let's look at the following problem. Do problem number 60. Right, this is a integral. So the antiderivative of this function, right? It's going to be arc. It's going to be arc cosine. Yeah, arcsine p, and evaluate at 2 endpoints. My question is, what is the value of it, right? I think it's going to be pi over 4 minus negative pi over 4. So it's going to be pi over 2, which is 3 pi, okay? I know sine pi over 4 is going to be square root 2 over 2. This is just a square, 1 over square root 2. That's the reason I got this, okay? And similarly, okay. So 3 pi is a value of the function. Okay, so the next problem, 64. Okay. Right, so sine x over cosine, to solve this problem, I think we should use substitution. Okay, we let u to be cosine x. Then du equals negative sine x dx. We see that when x equals 0, u equals 1. When x equals pi over 2, u is going to be 0. Right? So the integral becomes first of all u squared sine x times dx. Sine x times dx is this part will be negative du. But when x equals 0, u is 1. When x equals pi over 2, u is 0. Okay, why when is below the 0? That's okay. Now, if we interchange the interval as a limit, right? So you get positive sign. So now the antiderivative is going to be arctangent u. So evaluate the two endpoints. Arctangent 1, arctangent 0. Arctangent 0 is 0. Arctangent 1 is pi over 4. You have to be very familiar with the values. Okay? Like, because tangent of pi over 4 is 1. That's why arctangent 1 is going to be pi over 4. Okay? Yes. There, but we also we have to also consider arcsecant and cosecant functions because there are some integrals we have to deal with. It's not in the form 1 over 1 plus x squared, 1 over square 1 minus x squared. Okay, we have to consider y cos arc cosine x and cosecant x, secant x. Okay. So let's take a look at secant x. The secant x itself, it's not an inverse function. It's not an increasing function. I don't remember the graph, but I look at the value of sine. This is going to be 1. Oops. This is going to be 1 over cosine x, right? So I only memorize the possible values for cosine x. Okay, too much, okay, to memorize. So you memorize cosine, sine, and those are two essential functions. So cosine, when it's 0, cosine is going to be cosine 0 is going to be 1. But when x increases, cosine x decreases. Okay. So here's a line. Here's a pi over 2. Negative pi over 2. So the graph looks like that. Looks like a parabola passing through that. That's not enough, okay? Then we have another piece. Here's 3 pi over 2. This is a complete graph. It's periodical, okay? It's periodical. Now we have trouble, right? How do we find the pieces we use to find the inverse function? Okay. We decided to choose those two pieces. One is this part. Okay, but then it said, well, maybe nature we can from 0 to pi, right? Then as a piece, but actually we use this piece. Okay. So this is the two pieces, the function we're going to consider. So x is between for secant, right? For secant x, x is between 0 and oops. Between 0 and this is open interval, and x is greater than pi, less than 3 pi over 2. Oops. Okay. So the value, the y value is always the y value, absolute y value is always greater than 1, as you can see that. So now we can find so the interval right now is broken. That's right. The domain of the function is broken, but at least it's monotonic. You know, it's not always increasing, but at least it's a one-to-one function. So for any x, you can get the y value, right? Okay. And for any x here, you can get the y value, and they can reverse the procedure. Okay. So this is going to be, yeah. So y equals secant x, and same as x equals secant y, and you can draw the graph. Yeah, the inverse of y. Then you get the function y equals secant x. Okay. Because the y value here is greater than or equal to 1, and the x could be in any of these intervals. But here, yeah, this x will be greater than 1, but the y value will be either between 0 and pi over 2, or, yeah, here's x. X is in the interval from 0 to pi over 2, and from pi to 3 over 2. Okay. And, yeah. All right, so what we get here is a derivative of the arc as secant x is going to be this. Okay. Yeah, so this is a new function, right? Yeah. And similarly, you can define the arc cosecant x, and you can similarly define arc cosecant x. Right. Now the interval I'm not taking the interval. So arc cosecant. By similar argument, you can define this, then you can show that the derivative is going to be that. Okay, we are not going to show you how to find the derivative of this too, but this is what we need. Okay. All right, now we go back to the problem. Okay, evaluate the integral. At 69. Yes. All right, so when you see an integral like that, let's suppose it's on the test, right? What do you have to do? I think it's pretty tricky here. So we use an integral here as a let u to be square x. Let's try and use this as a substitution. I'm trying this substitution. So du equals this. Then this also implies that x equals u squared, right? So now the integral become that is going to be 1 plus u squared. Dx of x is going to be twice of du, okay? Because this implies. Okay. Right? So put the integral symbol on that. And that's going to be 2 times arctangent u plus constant. What is arctangent to u? U is going to be square x plus constant. Okay. So now let's look at this. This is very similar to one we see, right? We recall the derivative of arcsecant x. It is going to be x squared minus 1, right? Okay, so the only small difference here. Only small difference. So what we do is we're going to use substitution to modify the function. Right? So I let x to be 2u. Then dx equals 2 du. Right? So the integral is going to be x is 2u, here's the 2u squared, so 4u squared minus 4, and dx is 2 du, right? So I take 2 out, x is 2u, so 2u here, and the dx is 2 du. So that is already cancelled out. It's going to be 2u square minus 1 du. Okay. Then you can apply the above formula. It's going to be half of secant plus arcsecant plus cos. And the u is going to be half of x. Number 65. Well, okay. So what we can do with this? Okay, we have to use some. We have to simplify this integral, right? possible substitution, but you don't like this arcsine x. So let's try this to see if it works. Okay, so you let u to be arcsine x, and then du equals of this and dx. So derivative of arcsine x is going to be 1 over square root of 1 minus x squared. Okay, that's good. So now the integral becomes just u du. Okay, just u du, and that is going to be natural log of a u plus constant, and this is just equal to arcsine x and plus constant. Yeah, you have to put up a absolute value on that because it's possible. It is it's negative. Next question. I want you to try this. All right, so you compare with this integral, right? This is going to be arctangent x plus constant. So what's the difference between? Okay, there's a 1 plus x to the 4th power, right? X to the 4th power, but anyway, so x, this is going to be x squared square, right? So it's very natural you let u to be x squared. If you do that, then du equals 2x dx. All right, so almost done. So the integral of x dx, 1 plus x to the 4th power, this is just u squared. And next time dx is half of du. Right. Then you get arctangent u plus constant. And arctangent u is going to be u is going to be x squared, so it's plus constant. Right, so this is what we get. I think I did all the problems. I hope it's enough.